Okay, let's talk about learning. Think about all those physical skills you've picked up over the years. Maybe finally getting the hang of riding a bike or perfecting a golf swing, even just typing without constantly looking down. How does your brain actually figure that out? How do you go from those first awkward, clumsy attempts?
Where you're thinking about every single little thing.
Exactly. To that smooth, almost effortless performance where it just
It's one of
happens.
those amazing things our bodies and brains just seem to pull off, isn't it? Often it feels like magic while it's happening.
Totally. And that whole process, that's what we call motor learning. It's not just about getting better right now in this practice session. It's about really acquiring and refining movements through practice, through experience. And it leads to, well, a pretty permanent change in your brain's ability to actually do the skill.
The wiring is actually changing. It allows for that skilled behavior to stick around.
Yeah, and the source material you share, it puts it nicely. It's how your brain encodes these actions, eventually making them automatic.
Stored away for quick recall.
So our mission in this deep dive, tailored specifically for you using your sources, is to unpack some of the big theories that try to explain this incredible process.
Right. We're going to look at three main frameworks.
We'll hit Adams's closed loop theory, then Schmidt's schema theory, and finally the more recent ecological approaches.
And just to set the stage, we should probably quickly touch on the general stages of learning most people go through.
Good idea. The cognitive, associative, and autonomous stages.
Exactly. They help frame where these theories fit in.
Okay, sounds like a plan. Let's dive right in. First things first, just so we're all grounded, what exactly is motor learning at its core?
Well, like your source highlights, it's fundamentally an internal thing, a neurological process. It's not the temporary improvement you might see just during practice. It's a more lasting change.
Right, a potential to perform better.
Exactly.
Yeah.
A relatively permanent change in your capability for skilled movement. And it comes about because of practice or experience.
Hmm.
You can almost picture your brain rewiring itself, strengthening pathways so you can run that skill automatically without the step-by-step conscious effort.
Like learning to drive. Intense focus at first.
Oh, yeah. Total concentration. But
That'll be.
you can chat, listen to music,
Yeah.
hopefully still pay attention to the road.
Huh. Yeah, let's up the drivers well into the autonomous stage for that. Okay, so if it's about practice, why do we even need theories? Isn't it just practice makes perfect?
Well, practice makes perfect is catchy, but it doesn't tell you much, does it? It doesn't explain how practice works or why it works, or even what kind of practice is actually best. These theoretical frameworks, they're like essential guidebooks. They give us structured ways to think about the mechanisms underneath.
Okay.
Things like, how do we form these motor programs? How do we spot errors? How do we adapt a skill, say throwing a ball, to different distances or weights?
Right, the nitty-gritty.
Exactly. And understanding that helps coaches, therapists, anyone teaching a skill move beyond just guessing. It helps you make informed choices for the learner.
That makes a lot of sense. Okay, and before the big theories, your source mentioned those general stages people go through. Can you walk us through those quickly?
Sure thing. It's a really useful model, often credited to Fitz and Posner. 3 stages. First up is the cognitive stage. This is ground zero, beginner level.
Trying to figure it all out.
Totally. You're focused on just understanding the basics. What's the goal? What are the main movements? Your performance is usually pretty inconsistent, jerky, lots of errors,
Yeah.
but we'll often see big jumps in improvement early on.
Because you're starting from nothing.
Pretty much. You rely heavily on thinking consciously, listening to instructions, watching someone else do it. It's problem-solving time. Your source calls it the fake it till you make it stage.
I like that. High mental effort.
Definitely. High cognitive load. Then you move into the associative stage. Now you've got the basic idea. You start refining the movement pattern. Less conscious thought is needed for the core actions.
So you can focus on the detail.
Exactly. Making finer adjustments. Performance gets more consistent, smoother, more efficient. The gains might not look as massive as in stage 1, but they're steady. And feedback here, both how it feels internally and the actual result, like did the putt go in,
Yeah.
that's super important for fine-tuning.
Things start becoming a bit more automatic.
Right. Cognitive demand drops. And this stage can last a long time, even for experts who are always tweaking things.
Okay, and the final stage.
That's the autonomous stage. The school is now largely automatic. It just happens.
Like walking and talking.
Perfect example. Performance is consistent, efficient, accurate, and it doesn't get thrown off easily by distractions. This comes after a lot of practice. Think of that musician playing effortlessly, or the driver navigating complex traffic. You can allocate your attention elsewhere now, to strategy, to conversation, whatever.
Wow. So your brain's direct involvement really shifts, doesn't it? From very deliberate, explicit control early on
Mm,
to much more implicit, automatic execution later.
precisely. And knowing which stage you or your student is in has huge implications for how you should teach or practice. What helps early on might actually hurt later.
Okay, great foundation. Now let's really get into the theories about how this all happens. Your source kicks off with Adams's closed loop theory. What's the big picture?
So back in the 70s, Jack Adams really zeroed in on the role of sensory feedback. Information coming back from your body during the movement is called closed loop
Mhm.
because there's this continuous cycle. You act, you get feedback, you adjust, you act again, like a thermostat system.
Right, constantly checking and adjusting. And his theory had two key parts, these traces.
That's right. Two types of memory traces. There's the memory trace, which is fairly simple. It just selects and kicks off the movement.
Yeah.
But the crucial one for learning, in Adams' view, is the perceptual trace.
Okay, what's that?
Think of it as an internal reference of correctness. It's built up slowly over many practice trials from the sensory feedback you get during successful movements. It's the memory of what the movement should feel like, especially when you reach the correct endpoint.
Ah, so learning is like building up this internal feel for doing it right.
You got it. And the mechanism for strengthening it is error detection. You compare the feedback from your current attempt against this ideal perceptual trace. If there's a mismatch, an error, you use that information to make corrections, either during the movement, if it's slow enough, or for the next try. It's all about reducing that error signal.
This sounds like it would work best for certain kinds of movements then.
It really does. The theory is particularly well suited for slow, precise positioning tasks. Think like tracing a line carefully, or moving your finger slowly to a specific target.
Tasks where you actually have time to use that feedback while you're still moving.
Exactly. Time to process and adjust midstream.
So, based on this, what was Adam's recommendation for practice?
It logically follows that he advocated for very specific, highly repetitive practice of the exact correct movement.
Just drill the same thing over and over.
Pretty much. The idea is to hammer in that correct perceptual trace. Errors were seen as detrimental because they might strengthen the wrong trace. So practice the identical movement to the same precise endpoint.
But, I mean, human movement is way more varied than just slow, precise stuff, right? What are the big limitations people pointed out?
Oh, significant ones, yeah. It really struggles with fast, ballistic movements, like a tennis serve or a punch. Those are over before you can really use feedback during the action to correct them.
Right, feedback comes too late.
Exactly. It also has trouble explaining how we learn when feedback is missing or reduced. And a major issue is the novelty problem.
How you do something new.
Right. If you need a perceptual trace based on past correct movements, how can you possibly perform a movement you've never done before accurately the first time? Where does that initial trace come from?
Good point.
And then there's the storage problem. If you need a separate memory trace and perceptual trace for every single tiny variation of every movement you can make, well, the brain's storage capacity seems like it would be overwhelmed pretty fast. It just doesn't seem practical.
Okay, so Adams laid some groundwork, focused on feedback, but definitely had those gaps, storage and novelty being big ones. Is that where Schmidt's schema theory comes into play?
Yes, precisely. Richard Schmidt, in 1975, proposed his schema theory specifically to address those key problems. He wanted a more flexible explanation for how we learn and control the huge variety of movements we make, including new ones.
Okay, so how does Schmidt get around that storage problem, needing a memory for every single movement?
His big idea was the Generalized Motor Program, or GMP. Instead of storing countless specific movement instructions, he suggested the brain stores abstract, general blueprints for classes of action,
Classes
like a general program for throwing, or one for walking or kicking. These GMPs capture the fundamental pattern, the basic timing and sequence. They have what he called invariant features, things that stay relatively consistent every time you perform an action within that class. For throwing, it might be the order of arm segments moving or the relative time each part takes.
Okay, so the GMP is the core structure, the basic throwness of a throw.
Exactly. It's the general template, but obviously you don't throw a softball the same way you throw a dart.
Right.
So, to produce a specific movement from that general class, you apply parameters to the GMP. These are the adjustable bits, things like the overall force, the overall duration or speed, maybe even which specific muscles get used.
So you take the basic throw in GMP and tweak the parameters for a hard, fast ball versus a gentle toss.
Precisely. Same underlying program, different parameter settings.
Got it. GMP is general, parameters make it specific. But how do you know which GMP to use and what parameter values to plug in for a particular situation?
That's where the schemas come in. These are not memories of specific movements, but more like abstract rules or relationships that you develop through experience. Schmidt proposed two key schemas. First, the recall schema. This operates before you move. It takes the current situation, the initial conditions, like where you are, where the target is, and what you want to achieve the response specifications. And it uses a rule to select the right GMP and the right parameters to achieve that goal.
So it helps you plan the movement. Given X, do Y?
Kind of, yeah. It answers, what specific settings do I need for my GMP right now?
Okay, and the second schema?
The recognition schema. This one is used during or after the movement to evaluate how it went. It's based on relating the parameters you chose, the sensory feedback you actually received during the movement, and the final outcome, did you hit the target? Did the ball go where you wanted?
Knowledge of results, right, KR.
Exactly. Schmidt emphasized knowledge of results, the external feedback about the outcome. The recognition schema uses all this info to help you assess success and, crucially, to update your system for next time. Did those parameters lead to the expected feeling and the desired result?
I see. So learning, in Schmidt's view, is about refining these rules, these schemas, making them better predictors and evaluators.
That's the core of it. Every time you make an attempt, you gather 4 pieces of information: initial conditions, parameters used, sensory consequences, and the outcome, KR. This data strengthens and refines both the recall and recognition schemas. And the more varied your practice experiences are, the richer the data set for building these rules, making your schemas more robust and flexible.
And that's how it tackles the novelty problem.
Yes, that's a huge advantage of the theory. You don't necessarily need to learn a brand new GMP for every variation. If a new movement falls within an existing class, like throwing something unusual, you use your established schemas to estimate the right parameters for the existing GMP based on the new situation.
So you use your throwing schema, built from throwing balls and stones, to figure out how to throw, say, a crumpled piece of paper into a bin for the first time.
Exactly. You interpolate or extrapolate from your existing rules.
Okay, this is really interesting, because the advice for practice that comes out of Schmidt's theory sounds like the complete opposite of Adams.
It's a massive shift. Probably the most influential practical implication of schema theory is the importance of practiced variability. Meaning, practicing a skill under a wide range of different conditions is generally better for learning, especially for long-term retention and adaptability, than just repeating the exact same thing over and over.
So vary the speed, the distance, the weight, the context.
All of it. This forces your schemas to become stronger and more flexible because they have to work with a wider range of inputs and outputs.
Like the basketball player practicing shots from all over the court, not just the free throw line.
Precisely. It prepares you for the unpredictability of real-world performance. Your source mentions the contextual interference effect here, too.
Right, mixing things up in practice.
Yeah, practicing different skills or variations in a random order often leads to better learning than practicing them in separate blocks, even though it feels harder during practice. It makes you work harder to retrieve and reconstruct the solution each time, which strengthens the schemas.
Although the source did note that maybe some constant practice isn't bad, especially early on.
True. There's nuance there. Maybe you need some consistency initially to get the basic GMP down before introducing lots of variability. It's likely a balance.
Makes sense. So what are the main criticisms or limitations leveled against Schmidt's theory? It sounds pretty powerful.
It is powerful, but it's not perfect. One challenge is still the bootstrap problem. How does the very first GMP for a totally new class of movement get formed? Before you have any experience to build schemas on, where does that initial template originate?
The origin story.
Kind of. Also, the exact mechanisms of the recognition schema, how it works and what sensory info it uses, have been debated and aren't fully pinned down. And some argue that relying on these abstract schemas can still be quite cognitively demanding, especially in the early stages of learning, maybe more than the theory fully accounts for.
Okay, so we've gone from specific traces in Adams to generalized programs and adaptable rules in Schmidt. Now, the third perspective. Ecological approaches. This sounds like a completely different ballgame.
It really is. It's less focused on detailed blueprints inside the head and more on the whole picture, the performer interacting with their surroundings. It views movement not as something dictated solely by an internal command center, but as something that emerges from the dynamic interplay between you, the task you're attempting, and the environment you're in.
So the context, the situation, is really front and center.
Absolutely. The fundamental idea is that your behavior arises from the constant interaction of three things. The individual, your body size, strength, fatigue level, motivation. The task, the goal, any rules, the equipment you're using, and the environment. Gravity, the surface you're on, the lighting, maybe even other people. Functional movement patterns aren't seen as being retrieved from memory, but rather as self-organizing solutions that your system discovers based on the constraints imposed by these three elements.
Your source had that striking quote. All the information you need to act already exists in the environment. That really flips the script from internal programs.
It totally does. It emphasizes direct perception. The idea is you don't necessarily need to build a complex internal model of the world, process it, and then compute a motor command. Instead, you directly perceive the possibilities for action that the environment offers you, given your current capabilities. These are called affordances.
Affordances.
Yeah, like a chair affords sitting for an adult, but maybe it affords climbing for a toddler. A gap affords crossing, if it's small enough relative to your jumping ability. You perceive these opportunities directly. This ties into the idea of perception-action coupling. Perception guides your action, and your action changes your perception in a continuous loop. You see the gap, you jump, landing changes your view, guiding your next step.
So learning isn't about perfecting an internal plan, but getting better at tuning into the environment and finding effective actions.
Exactly. Learning is viewed as a process of exploration and discovery. You're actively searching the possibilities, exploring your perceptual motor workspace to find stable, functional solutions that achieve the task goal within the current constraints.
Constraints aren't necessarily bad here.
Not at all. Constraints from the individual task or environment actually shape the movement possibilities. They define the problem space. And a key practical application here is the constraints-led approach, CLA.
Where you manipulate those constraints.
Right. A coach or therapist might change the size of the playing area, the weight of the ball, or the rules of the game to sort of nudge the learner towards discovering more effective movement solutions for themselves. The goal isn't necessarily to repeat the exact same movement pattern every time your source mentions repetition without repetition. It's about achieving the task goal consistently and adaptably, which might involve slight variations in movement each time. Variability isn't error, it's exploration.
This feels very intuitive for learning complex skills in dynamic, real-world settings. What are the main strengths?
It's fantastic at explaining adaptability and how skilled performers seem to just do the right thing in unpredictable situations, like sports. The emphasis on perception-action coupling is a huge strength. It also provides a really strong basis for designing effective learning environments that encourage exploration and problem-solving, like the CLA. And the concept of self-organization is powerful for explaining how new movement patterns can emerge spontaneously without explicit instruction.
Okay, any limitations or criticisms?
Some critics feel it's less precise about the specific internal neurological mechanisms compared to theories like Schmidt's. Concepts like self-organization or attractor states can feel a bit abstract or harder to pin down for making very specific predictions.
Harder to write a step-by-step recipe.
Maybe, yeah. Your source notes it can seem not easily applied to specific examples if you're looking for that kind of detailed prescription, though the CLA offers very practical tools. And some might argue it potentially underemphasizes the role of internal cognitive planning or explicit strategies, especially for very complex multi-step tasks.
Okay, wow. 3 really distinct ways of thinking about motor learning. How do they stack up against each other when you compare them directly?
They really differ on fundamental points. Let's look at a few. First, what gets stored or learned? Atoms. Specific traces for exact movements. Schmidt. Generalized programs, GMPs, and abstract rules. Schemas. Ecological. Less about stored prescriptions, more about refined perception-action pathways or stable attractor states.
Big difference there. What about the role of feedback?
Also quite different. For atoms, feedback during the movement is essential for real-time correction. For Schmidt, feedback, especially KR after the movement, is mainly for updating the schemas. For ecological views, sensory information isn't just feedback about errors, it's guiding information that directly shapes exploration and constrains future actions in that perception-action loop.
And the kinds of skills they seem best at explaining.
Atoms fits best with those slow, precise, self-paced tasks. Schmidt is really strong for skills that need adapting to varied conditions, learning general rules you can apply flexibly. Ecological approaches excel at explaining complex, adaptive skills in dynamic environments where learning happens through exploration and finding solutions.
And the most practical difference, the practice recommendations.
Yeah, that's stark. Adams points towards exact repetitive practice, minimize errors. Schmidt champions variable practice, experience different conditions to build robust schemas. Ecological approaches also favor variability, but frame it as exploratory practice, manipulating constraints, seeking functional solutions, repetition without repetition.
Your source had that great example comparing them using buttoning a shirt. Can you recap that? It really highlights the differences.
Yeah, it's a simple but effective illustration. So, learning to button a shirt. An Adams approach would mean practicing with the exact same shirt and the exact same buttons over and over to perfect that specific sensory trace.
Oh,
A Schmidt approach would involve practicing with that shirt, but also maybe shirts with slightly different sized or textured buttons. Same basic action class, but varying the parameters builds a stronger schema for buttoning.
right. More flexible rule.
Then, an ecological approach, using the CLA, might involve practicing with totally different styles of shirts, different button types, maybe while sitting, standing, in dim light, using different fabrics. The focus is on exploring how to achieve the goal, button fastened, successfully under various realistic constraints.
Wow, that really drives home how the underlying theory directly shapes what you'd actually do in practice.
Absolutely. Your theoretical stance really matters for application.
And this isn't just academic navel-gazing. These theories have massive real-world implications, right?
Huge. In sports coaching, for instance, Schmidt's ideas about variable practice are pretty much standard now for developing adaptable athletes. And ecological ideas, especially the constraints-led approach, are hugely influential. Coaches design drills that manipulate rules, space, or equipment to encourage players to discover solutions themselves.
They become guides, not just instructors.
Exactly. Though principles from Adams, like focused repetition, might still have a place for refining very specific technical details, maybe in sports like archery or diving. Good coaching often blends ideas.
And what about physical rehabilitation? Seems crucial there.
Oh, it's absolutely fundamental. Therapists rely on these principles constantly. Schmidt's work supports practicing functional tasks, walking, reaching under varied conditions, different surfaces, object weights, so patients can generalize the skill back to their everyday lives. And ecological approaches are really shaping modern rehab. Therapists manipulate task constraints, like the height of a chair you're getting up from, or environmental constraints, like walking on uneven ground, to help patients rediscover functional movement patterns within their current abilities.
Focusing on the task, not just the muscles.
Right. Using implicit cues, reach for the cup, rather than explicit instructions, extend your elbow. Your source also rightly mentions feedback. It's vital. But reducing how often you give it over time helps foster long-term learning and stops the patient becoming dependent on the therapist's cues.
Makes sense. Any relevance for workplace skills or ergonomics?
Definitely. Ergonomics programs trying to teach safer movement patterns often use structured training based on motor learning principles, active practice, feedback, gradual progression, as your source notes with that four-stage model example. An ecological perspective reminds us that safe lifting isn't one single technique. It depends on the individual worker, the load, the space. So training should involve practicing lifting varied objects, getting feedback, building adaptable, safe strategies, not just watching a video of the one right way.
It really seems like understanding these theories helps you think differently about how you learn, how you might teach or coach, or even how you design a task or environment.
It totally reframes how you look at skill acquisition.
Yeah.
It's not just mindless repetition.
Okay, so wrapping things up, we saw Adams focusing on feedback and specific traces for correctness. Then Schmidt gave us generalized programs and schemas, explaining novelty and really highlighting the power of practice variability.
Right, a big step forward.
And finally, the ecological views shifted the focus dramatically to the interaction between the individual, task, and environment, seeing learning as exploration and discovery within constraints.
Three quite different lenses.
And it seems clear that no single theory has all the answers, right?
Absolutely not. The field is really moving towards more integrated views now. Researchers are exploring how these different ideas might fit together, how explicit cognitive strategies interact with more implicit motor adaptation. There's also a lot of interest in the specific role of different types of errors in driving learning and trying to understand the underlying neural mechanisms better.
And new approaches are still pushing the boundaries.
Yeah, like differential learning, which your source touches on. It encourages even more variability, sometimes deliberately introducing movements that might seem wrong under other theories, based on the idea that this broader exploration helps the system find robust solutions. It resonates strongly with ecological ideas.
So the future looks like building more comprehensive models, figuring out the brain basis, optimizing practice by blending principles.
And crucially, making all this complex theory truly practical and usable for people learning skills in the real world, whether that's an athlete, a patient recovering from stroke, or just you trying to learn a new hobby.
Exact.
So it really leaves you with something to think about, doesn't it?
Which is,
Well, if learning involves both nailing down consistent movement patterns and being able to adapt them flexibly, how should you approach learning your next skill? How might you balance that focused, repetitive practice that builds reliability with a more varied, exploratory practice that builds adaptability? Where's the sweet spot for you or for someone you're teaching?
hmm, finding that balance between consistency and flexibility. That's a great takeaway.
It's the ongoing challenge.
Well, that was a fantastic deep dive into the world of motor learning theories. Hopefully, this exploration helps you appreciate the amazing, complex processes firing away in your brain every single time you learn or perform a physical skill.
It really is remarkable when you stop and think about it.
Definitely keep that question about balancing practice types in mind. It might just give you a new perspective on your own learning journey.